Hi, David.
Hi.
You're the first to show up.
I didn't think I was that early.
Oh, no, you're not early. But nobody's showing up. I wonder why. Do you find the lecture useful?
Yeah, I find it useful to listen to it, and then I go back and check the notes after to review, because I can't.
Okay.
I don't. It's hard to take it all in at once.
I was saying that my notes are too good, so they don't need to come to lecture. You can just read the notes. Okay. Let's wait just one more minute. Oh, I have another person joining us. Hi, Jason. So today, I'm going to give a lecture on computational electromagnetics and numerical methods in solving Maxwell's equations. This is a pretty important topic because more often than not, you will be using a commercial numerical software to solve Maxwell's equations rather than solving those equations yourself. So a group of highly trained PhDs have spent many years developing computational algorithms and knowledge so that these equations can be solved now on commercial software. And since Maxwell's equations have been tested and time tested to be very accurate, sometimes it will say that if you go to the lab and perform an experiment, and if the experiment is not agreeing with your calculations, you better trust the calculations more and then ask your graduate students to go back to the lab and do the experiments again. That is the faith that scientists and engineers have in Maxwell's equations these days. So we see how we can solve these equations as accurately as we can using different kinds of computational methods. This would be a very brief overview of a field that has developed in the last few decades, but at least it gives you a handle on what this knowledge is. And if you were to use commercial software, you know what you're doing. Okay, so there are essentially two kinds of equations that we solve in electromagnetics. One is actually differential equations, the other one is integral equations. We do not encounter integral equation that much, but we have encountered lots of differential equations. Like if we started out with Maxwell's equations, let me see, why is it not writing today? I don't know why it is not writing today, but let me reboot my PowerPoint and see if it does any good. Well, does anybody remember how to switch the pen into a writing mode? Because I remember I have to go through many of these buttons and switch one of them into a writing mode, and somehow it got switched. That is, there's a genie in the computer always, and if you come back the next day, some of these buttons got switched. I don't recall where the button is. Does anybody know?
I think you should be able to hit that, that black
That one?
pen and try writing now.
Okay, let me see. Okay, good, thank you. Yeah, that thing got unswitched. Okay, thank you. And so we have lots of differential equations in electromagnetics. For instance, if we have a Helmholtz wave equation, this essentially is a differential equation. Or if you have Maxwell's equations, you can reduce it to something that looks like a differential equation, like curl of E minus k square E is I omega mu J of R or something. Okay, I'm using E to the minus I omega T time convention again. And these are all differential equations that we have to solve. And it's less frequently that we encounter integral equation. So how do we solve these integral equations? You can write this integral equation or differential equation in an abstract fashion and say that they are all of the form of LF equals G. This is an abstract mathematical form where this is a linear operator. And this linear operator in this case can be like Laplacian square plus k square. Okay. And in the second case, it could be curl of minus k square. Okay. In the first case, that operator operates on the field phi of R. And then the second case, it operates on the vector field E. So my F can represent the scalar wave function phi, or my F can represent the vector wave function E. Okay, those are all the things that we have. And of course, this is known as the scalar wave equation. And then this is known as the vector wave equation. Okay. So the goal of this chapter or this lecture is to teach you how to convert a linear operator equation into a matrix equation. I would like to further say that the right-hand side G in this equation can be Q for the scalar wave equation, and then G can be I omega mu J of R in the vector wave equation case. The goal of this lecture is to figure out how to convert this equation into a matrix equation so that we can feed this to the computer. Computers can only recognize matrix equations. Computers cannot recognize an abstract mathematical equation like this, and we have to figure out how to go from here to there. Okay. So before we move on, I'd like to point out the fact that we have integral equations as well. Integral equations are equations where the unknowns are buried inside a integral. For instance, if I have an equation written like this, where g might be the Green's function, okay, this will be called an integral equation. And you know that this is of the form of L f equals g as well, where g is this thing, f is that thing, and my L operator is that Green's function operator over there. Okay, and this Green's function is usually called a kernel in the language of the integral equation people, and the unknowns to be solved for is actually f. Okay, and this is usually the known function, or if you look at it from matrix theory, it's the driving term of this equation. Okay. So what are the example of volume integral equation? The simplest example I could think of is actually a solution of a scattering problem called the volume integral equation. Say if we have a scalar wave equation to solve, and the scalar wave equation is not that simple, but involving inhomogeneity in the wave number. Okay, this is inhomogeneous. Or involves inhomogeneous medium. Okay, and then how do we solve this equation and cast it into a form that computers can digest them? Well, the way to do that is actually to rewrite this equation into a form that you can derive an integral equation from. The way to do that is actually to assume that you have a scattering problem where k squared r is inhomogeneous inside the scatterer, but k squared r is equal to k naught squared outside the scatterer. And that if you have a source q of r over here, and it generates an incident wave. And then the incident wave will impinge on the scatterer and give rise to a scattered wave. Okay, so I can rewrite that equation that I have that elucidates this physics more properly by saying that I can rewrite it as k squared r minus k naught squared I introduce a k naught square on the right hand side, sorry, on the left hand side, and so I should introduce a similar term on the, let me see, did I do it right? Yes, I have. Let me see, did I do it right? Okay, I'm doing it right. Okay, so I introduced a k naught square term on the left hand side. I better introduce one on the right hand side, and then I can rearrange this equation to look like phi of r, q of r, and then I take the other term to the other side of the equation. Okay, so far so good. I'm just rearranging terms. But I can now think of this as equivalent sources. And these equivalent sources, the first one is well defined. QR is what I have that generates the incident field. The second one is actually only non-zero over here. okay, k squared minus k naught squared is not equal to 0 inside V when R is part of V. Okay, so this term is only non-zero inside the scatterer, and they can be thought of as equivalent sources inside the scatterer. And now I can use the principle of linear superposition, saying that if I know how to solve this problem by the Green's function method, okay, if I know how to solve the point source response to this problem, then I can use the principle of linear superposition, saying that this is the same as the convolution of the Green's function with the first term on the right-hand side. Okay, so actually this is over this volume over here. And then the second term would be the convolution of the Green's function with k squared minus k naught squared phi of r prime over V. Okay, can you see that? I have written this equation in such a way that everything is in terms of integrals. Okay, and this first term is the field generated by Q in the absence of the scatterer. So I would call this the incident field. Okay, the second term is due to the fact that I have an inhomogeneous medium here. That inhomogeneous medium makes this term non-zero. When I integrate this, I only need to integrate over the volume of this scatterer, and this will produce a scattered field. This would not have been there if the scatterer is absent. If k squared r is k naught squared everywhere, this term would have been 0, but it's not equal to k naught squared inside this V, so it contributes to the term which I can call the scattered field. So if I rewrite this equation now, I put the known quantity on the left-hand side, and then I can have minus VR on the right-hand side. And then I would have, let me see, k squared minus k naught squared plus GR prime, k squared minus k naught squared phi of r prime on the right-hand side. So you see that the unknown is this quantity over here, and the unknown is also this quantity over here. And this equation can be termed as an integral equation because the unknown is buried inside the integral as well as the outside the integral. This actually is called the Fracom integral equation of the second kind if you want to use mathematical language. So you can see that this second term is the linear operator. It's a linear operator, and hence I can write this equation as being a phi incident R is equal to a linear operator operating on this field, the unknown. Okay, I have this as the unknown on the right-hand side. So this again is an equation of the same form as I started out with. I have an LF equals G, then this is my F, this is my G, and I have a linear operator equation to solve. And if I figure out a method of converting this linear operator equation into a matrix equation, then I can feed that to the computer, okay? And you can do this for a surface integral equation as well, which is what I will not discuss. It can be done using equivalence theorem. It's discussed in the lecture notes. Okay, and I will not go into the detail, but let me just say that it can be done. And finally, you will have an equation that also is similar to what we had before, a linear operator operating on an unknown f equal to g. So all the integral equations be it surface integral equation or volume integral equation, can be cast into a linear operator equation. So the same thing happens to differential equations. If you have differential equations to start out with, you can also cast them into a linear operator equation. Okay, so our task then is actually to figure out a way to solve these linear operator equations. And these equations are said to have been defined in the Hilbert space. Okay, let me see. This equation is an equation in the Hilbert space because this is a infinite dimensional vector. We take a very simple example that we have these equations over here. This is a scalar wave equation. In one dimension, it will be very simple. It might be something like d squared dx squared plus k squared times phi of x is equal to q of x. Okay, this is 1D. This is 3D. And you can think of this as my L operator, and this is my F, and this is my G. You can think of this in either one dimension or three dimensions, it doesn't matter. They can all be abstractly thought of as something like this. And I like to introduce a new concept that you should think of a function as a vector. It's the same as a vector. Okay, a function like any function in one dimension is a vector. Okay, why do we want to think that way? Because if you think about a function and if you want to feed it to the computer, you cannot feed it as a function such as this, where x is a continuum. Okay, this is continuum. And this would be a continuum. And computers cannot digest a continuum function very easily. So when we need to communicate with a computer, what we need to do is to think of function as a vector but being discretized. Like in signal processing, if I have this function, I can digitize it. I can actually sample this function at given locations and feed the computers only these values in digital signal processing. So this function is being represented by a vector inside the computer. So you can think of this function when it's digitized becomes that function over there, which is essentially a vector. But you can generalize this idea to a continuous function. Instead of digitizing as people in signal processing like to do, I can also use interpolation, which is that if I have a function, if I only has its value at certain discrete points, I can still think of it as being represented or representing a continuous function, provided that whenever I need points in between the digitized points, I just interpolate for them. Okay. You can also think of interpolation as a way to retrieve a continuous function from a discrete function. Okay, and this interpolation can be done in many, many ways. One way is just to use a linear interpolation. Another way is to use kind of a cubic spline, quadratic interpolation, and so on. But the point I want to get across here is that in the real world, when you want to talk to a computer, a function becomes a vector. And that vector is a finite dimensional vector. And we just store these values, and they will be stored as F1, F2, F3 inside the computer. Okay, so you have to think out the box and think of a function as a vector now. And what we then need to do next is that, let me see. You can extrapolate this concept to 2 and 3 dimensions. Okay, so instead of thinking a function f of x as a vector, you can also extrapolate this idea to 2 dimensions. That is, whenever if I have a 2-dimensional function, I can extrapolate them in this manner using these extrapolation functions. And this is like a 1D, this is like a 2D, and you can do that with meshes. You can put meshes in the computational domain and use them for extrapolation. For instance, if I have a scatterer, if I want to define currents on this scatterer, I can replace the surface of the scatterer with meshes. And then whenever I need to put a continuous function on the surface of this scatterer, I only give their values at discrete points on the surface. And from the discrete points, you can extrapolate or interpolate for the values of the function in between them. And this is actually how things are being stored inside the computer. And in the case of a 3D function, it's harder to envision. It's harder to envision, but what you have then is that you have tetrahedrons. So in 2D, you have triangles. And you can show that in the tiling theorem, any 2D surfaces, which are these 2D surfaces, can be tiled with triangles. And you can also show that once you have a 3D volume, the basic element, which is called the simplex, is a tetrahedron. Okay, so you learn very quickly now that in order to approximate things in 1D, you use a segment, a line segment. That means if I have a 1D function, I just break into segments called line segment and then define the functions on this line segment. In 2D, okay, you use triangles. And then in 3D, you use tetrahedron. Okay, these are called simplices. These things are all called simplices. Simplices are the simplest form of an element you can have in the n-dimensional space from which you can interpolate for the values of the function on them. Okay, so I just want to show that this can be done, and hence once you have a function that you have either in 1D, 2D, or 3D, you can represent them inside the computer quite easily using such concepts. And then the next thing is to figure out how to solve these equations. Okay, solve these equations, as I said before, there are 2 main types of equations: differential equation and integral equations. So in general, as I said before, the equations are written as LF equals G, and this can be from integral or differential equation, and mathematically this linear operator is usually written in this manner. It is defined to be a linear operator that maps from a domain space. Domain space is like something that the operator acts on, and this is called the range space. So you can see that this is a domain space inside the domain space of the operator. This is inside the range space. Okay, and a good example of this is your differential equation. And this would be your range space G, and this is your domain space F, and this is your linear operator L. Okay, so abstractly, you can think of two abstract spaces in the mathematical world called V and W. Okay, the L operator just maps the function from the domain space to the range space. This is the mathematical abstraction. Okay, it's a cartoon sort of. You have to think of this as a cartoon's picture to see what the mapping is. So as long as we know how to approximate these functions in a domain and the range space, then we can convert this into a matrix equation. And how do we convert this into a matrix equation? Let's talk about that. Okay. So how do we approximate an operator equation like LF equal to G with a matrix equation? Well, this method is what I call the subspace projection method. And to do that, what you do is that you let the function f be written as a summation of an approximate function. Okay, so this is called the basis function expansion. Usually this is called a basis function. And this can be in one dimension. If it is one dimension, then it would be just that. Okay. And for instance, if you're having a function in one dimension, if you define this function between 0 and a, you can use something called a Fourier series expansion. N pi x over L or something like this, or let me call this A, L, and n is equal to 1 to infinity. This is what we learned in Fourier series. You can think of the Fourier function as a basis function. And usually this is not good because we cannot fit this to the computer. Usually we truncate this series after a certain term. And usually say that many functions can be expanded in such a manner in terms of a Fourier series. But then this Fourier series are not good for computation. So instead, if we have a function f of x, then we sample them at discrete points. We know their values. And then we use triangle functions to approximate them. And they can be thought of as interpolatory functions called the head function, or the chapeau function in French. Okay, I have the spelling correct in the lecture notes. I might have spelled my chapeau wrong. Maybe it's like this. Okay, and the chapeau function is nothing but just a triangle function. You can superpose many of these triangle functions to approximate any functions in one dimension. And you can do that in 2 or 3 dimensions as well, okay? So we can do this quite nicely in 1, 2, and 3D. And what we have then is an ability to convert a linear operator equation defined in the abstract space. Originally, this equation is defined in an infinite dimensional space where you will have needed an infinite number of information to define it, but we're going to approximate it in the finite dimensional space. And then we would have to figure out how to find the approximation of this linear operator in a finite dimensional space. So what you do is to substitute this equation into the above. You substitute that into the above, then if I substitute, say, this equation into the above equation, then I would get something like AN LFN X is equal to G. N is equal to 1 to N. Okay, just by doing a substitution of this, assuming that L is a linear operator. You know what L being a linear operator means is that L F1 plus F2 is, let me be more explicit. Say if something is linear, then you can say that this is LF1 plus A2 LF2. This is the definition of what a linear operator is. And if L is a linear operator, once I substitute that and exchange the order of operator and the summation, I can actually write this in this manner because L is linear. And then the next thing we need to do is to figure out how to convert this into a matrix equation. What you do then is to test this equation with the testing function or the weighting function. And then I just multiply this equation by W of M G, okay, where W of M could be also a one-dimensional function. And then I define it in the same interval that I have before. And the inner product here means that Wm of G just means that it is the same as Wmx Gx. And this from A to B, for instance. So it would be like, it can be from 0 to L, for instance. It doesn't have to be from 0 to B, but over the space in which the function is defined. I can do the same thing to the left-hand side. And then if I do the same thing to the left-hand side and exchange the order of integration, order summation, then I will have this being equal to AN WM. Okay, I have W sub M. Somebody's trying to call me. I don't know if you can see that. What I have done is to actually take this weighting function into the innermost part and perform the inner product. This is called inner product, as we have learned before in electromagnetics. So I take the inner product only on the innermost form, and then I do the same thing to the right-hand side. And I choose my testing function. This is called the testing function, or the weighting function. Sometimes it's called a weighting function. I will choose M of them. M is equal to 1 to N. So I choose N of them so that I have N of them. And then if I look at my equation now, if I look at my equation, I started out with an abstract equation such as this one over here. After going through this procedure, I will end up with, let me see. Okay, I end up with the equation that says that this actually is something of the form of AN, LMN, n is equal to 1 to N is equal to BM, M is equal to 1 to N. Okay, now if I look at this equation, it is of the form of L dot A is equal to B. It's a matrix equation. Voila. I have successfully been able to convert an abstract linear operator equation that I have in this form into a matrix equation. I have illustrated on how to do this in one dimension. You can repeat this exercise. If this function is a two-dimensional function, you will have used triangular meshes and defining your basis function on the triangular mesh, or you can have this repeated for 3 dimensions. You can have this been repeated for 3 dimensions. Then there you will have to define your function in 3 dimensions using a 3D tetrahedral mesh and so on. Okay, so the important message to take home is that given any operator equation, LF equals G, even if this operator equation is defined in the infinite dimensional Hilbert space, you can project it into a subspace, which is defined in the linear algebra space. And then all the things that you have to deal with will be finite dimensional. For instance, L is n by n, A is n by 1, B is also n by 1. Okay, so these are things that you can feed to a computer. And once you can feed it to the computer, we can use the breakneck speed of a computer to solve this equation. Okay, so that is the essence of computational electromagnetics, where you start out with an equation derivable from Maxwell's equations or scalar wave equation. And once you have this linear operator equation, we figure out a way of converting this linear operator equation into a linear matrix equation. And this essentially is done by the subspace projection method, where you actually define a basis function, a set of basis functions, so as to make things finite dimensional. That is, given a linear operator equation, which is in the infinite dimensional space, you approximate it. So this should be thought of as an approximation. Okay, so this should be an approximation. You approximate with a finite basis set, and the approximation can be quite reasonable if you think of them as interpolatory functions. And once you have this approximation, you can have a matrix equation that ensues from the infinite dimensional linear operator equation. Are there any questions regarding this? Is this okay with everybody? Then, given the matrix equation, the next question we ask then is, how can we solve this matrix equation efficiently? So we all know how to do that now. How can we solve this matrix equation efficiently? And if you were to solve this equation, there are many, many CAN routines that have been developed over decades of our work. And if L is n by n, and you can find L inverse, and once you find L inverse, you can say that A is L inverse dot B. However, the cost of finding L inverse is expensive. You can use Kramer's rule. I think it's spelled Kramer's. Or you can use Gaussian elimination. And you know that the cost of inversion is proportional to n to the power of 3, which means that if n becomes very, very big, the cost of finding the inverse of a matrix is very, very expensive. And that is not the way we should be doing this problem. Instead, we want to cast finding the solution of this problem into an optimization problem. And you will find that by converting this equation, L dot F equal to G into an optimization problem, the cost is a lot less. So in order to cast this into an optimization problem, we have to define a function now, a cost function. And we can define the cost function for this problem to be something that is the transpose of this times L dot F minus 2F transpose dot G. I'm writing everything in linear algebra notation. And this cost function I is something that you like to minimize. And if you can minimize this function, it would be the same as solving the above equation 1. Okay, so if you minimize the I, you minimize I in this equation, it is equivalent to solving 1. Okay, how can we have some intuition about this? You can think of this as being very similar to one dimension. If you have a cost function that is something like this, say if I have a cost function like this, and then the minimum of this, as we know from high school algebra, is obtained by differentiating this minus 2g. And if you set this to 0, then the solution is given by x is equal to g. Okay, we can obtain the minimum of this cost function very easily in one dimension, but this is not one dimension, this is n-dimensional. This is n-dimension. So finding the minimum is slightly more complicated, but we can use variational calculus to help us find the minimum of this. So the idea is that if the minimum is given by f of 0, so if f of 0 is the minimum point, and if we were to perturb f to be slightly different from f of 0 by delta f, okay, if I were to perturb it from delta f, and if f sub 0 is in fact the minimum point, the perturbation would give rise to 0 values or second order value. In other words, we want to use the fact that this is a cartoon picture, okay? So there are all possible values of f that you can search for. And if you have hit the minimum point, then the cost function would be second order accurate in delta f. So this is very similar to the calculus concept in one dimension. So if I now plug it into here, I can take the first variation of this equation, and it will be delta f t dot L dot f of 0. And I hope you know how to take first variation for multi-dimensional variables. Okay, there should be two terms that come out from the first term. The other term is f0 dot L dot delta f. Okay, so if I take the first variation, which is something you can learn in variational calculus, and if you are not comfortable with that, you just plug this back into the beginning and do expansion and then collect the leading order term and the second order term. You will get this equation. Since I don't have time to do the thing in great detail, I will just use my knowledge of variational calculus and write down the first variation for you immediately. And then I notice that if L is symmetric, okay, if L is symmetric, then you can show that these two terms are the same as each other. If you take the transpose of this term, you get exactly that term, and so on. So the first variation can be written as being equal to 2f0 dot L dot, let me see, the two terms are similar, so let me pick the first term. Okay, the first term is delta f transpose dot L dot f0, and there are two of them, so I just put a factor of 2 in front. Okay, if the f sub 0 is in fact the optimum point, if f sub 0 is in fact the optimum point, the first variation about this optimum point or the minimum point should give rise to 0 variation in delta I. The delta I will only have second order variation and no first order variation. So this should be 0. Its first order variation should be 0. And now if you solve this equation, this would cancel each other. Okay, if you solve this equation, this would cancel each other. And you have this been true. So which means that the minimum point of this cost function is in fact the solution to this equation. So instead of solving this equation directly, you find ways to minimize the cost function. Okay, and how do we solve this minimization problem? You can use a gradient search approach. This is something that is been illustrated in 2 dimensions, but in 3 dimensions, it will be a lot harder to draw, but the idea is similar. You can do a gradient search in the multidimensional hyperspace and look for where the minimum point is. And it turns out that this way of solving the problem is a lot cheaper than using Gaussian elimination or Kramer's rule and so on. And you can actually solve this a lot faster. And even people in artificial intelligence and neural nets and so on, machine learning are solving minimization problem like this. So there's plenty of knowledge out there as to how we can minimize the cost function. I will not go into the detail of how to minimize this cost function numerically. It's been written up in many textbooks, including some of which I have written, okay? But it casts a solving for the solution of Maxwell's equation into finding the minimization or the minimum of a cost function. And this can be done a lot more cheaply compared to having to invert the matrix system. I will stop here. Are there any questions regarding the gist of computational electromagnetics? The gist is, of course, given the linear operator equation, you convert it into a matrix equation. And then if you have to solve this matrix equation, which can be very, very large, you cast it into a minimization problem instead of a matrix inversion problem. And then you find ways of solving this inversion problem or this matrix evasion problem indirectly. Okay. And if there are no other questions, I'll let you go. Okay. And thank you for coming and keep safe out there. Any questions? No? Okay. I'll let you go. Thank you for coming.